Okay, so far we've done quite a lot of concept. We've covered a lot of concepts up to data visualization, data manipulation, data cleaning, and all of that. And we want to move to building models. So if the goal of the project you are doing is to build a predictive model to help you make some predictions, then you are talking of machine learning. So I'm just going to give you a brief overview of machine learning, and then we'll move to some basic concept that you need to know when you're dealing with machine learning. I'm going to skip all the mathematics and all the statistics so as not to bore you, because normally there's a lot of mathematics involved. Yeah. So that's just it. So, but I'm going to skip all of that and move to the major concept that you need to know. All right. So, sorry, I think I stopped sharing my screen. Okay. So actually the things I wanted to know is like to be able to explain what machine learning is, and then you should be able to discuss the types of the machine learning, the process of building machine learning models, concept of overfitting, underfitting, and generalization. And then if time permits, I may move to, I may discuss linear regression, and maybe next week, or if time still permits, we may see some problems with linear regression and how to resolve the problems of linear regression. Okay, so what is machine learning? So apart from Dimeji or Sheung, apart from Dimeji, maybe I even want to hear from Sheung. What is machine learning? Anybody here except Dimeji for now. What is machine learning? What comes to your mind when you heard about machine learning? Awele, what do you think? Awele, are you there?
Oh, I thought I was unmuted.
No.
I said, like making computers learn to do things on their own without exactly telling them what to do.
Okay, that's a good point. Making computers do some processes on their own without explicitly programming them on what to do. Okay, who else? Fumbi, do you want to say something? Okay, Fumbi is not talking. Yes, who else? Sheung, what do you think?
Yes, sir.
Great.
Thank you.
I can't hear you.
I think it has to do with using algorithms to give instructions to the computer to carry out certain tasks.
Okay. Okay. All right. So that's a good one. So when we talk about machine learning, just to move in line, build on our last thought. So machine learning has to deal with, so let me give the overview. In the past, what programmers do is that if they want to perform they want to build a model, like maybe a model to categorize images as either cat or dog, what they would do is that look at the attributes of a cat and look at the attribute of dog, like maybe the shape of the eyes, the shape of the nose, the size, you know, the tail of that cat or dog, you know, or the shape of the head. So they will try to write rules, different rules. We can amount to 1 million rows. You can amount to millions of codes in terms of lines. You know, they would try to capture all the different rules in terms of the shape, the height, the eyes, and all of those, the nose. They will try to write all of these rules and give this instruction to the computer so that the computer can say, okay, when I see an image that have this particular attribute I've defined this way, it should be a cat. And if I see all the attributes that look this way, it should be a dog. So that's, but you know, it's very complex because there are different types of cat. If we go to Google now and type images of cat, you will see different varieties of cat. Different, some even cat look like dog, some dog look like cat. You know, I'm not talking about this your local cat or local dog. So there are different breeds of cat and dog, and so it becomes so complex. And so those kind of rules, they are susceptible to mistakes, to errors, you know, things like that. So because of that, those programmers or researchers began to look for better ways to they began to think in another line that instead of designing rules for the computer, can we allow the computer to design rules by itself? Can we allow the computer to come up with rules on their own that they will use to identify a cat from a dog? That's just one example. So those rules, they need to come from large amount of data. So you need to throw some portion of data to the computer and let the computer go into those data, go through them and come up with their own rules based on the variables in the data or the features in the data. Let them come up with their own rules to differentiate a cat from a dog. So the process of allowing machine or computer to use data, which we call experience, to make informed decision or to come up with rules without being explicitly programmed is what we call machine learning. I don't know if it's clear. Is it?
Yes, it is.
Okay. So that's what we call machine learning. It's just a process that is a process of allowing machine or computer to use data or experience to come up with rules. Those rules in mathematics, those are what we call function. If you have ever taken any calculus class before where they will put f of x equals to y, you know, those things, they just don't explain. It's a function. And the x is the data that you have been working with all this while. The y is the output, what you are trying to predict. That function is that rule that the computer comes up with to help you map the input to get the output y. Okay. Hello. So that is, so when it's just a pity that in our, education, they don't explain what those functions, what it means when they put f of x equals to y and you begin to memorize and all of that. So that's just it. So anytime you see x, you are talking of the data. And the data can have many features. What are the features? Those are the x1, x2. So x1 can stand for like maybe the weight, x2 can stand for like maybe the height or things like that. Those are the different features or the different variables in the data. And the y is what you want to predict, cat or dog, things like that. And if you are talking of maybe building a model to predict house prices, the Y becomes the price of a particular house. That is just it. Okay, so we've explained this is enabling machine to learn from experience without being explicitly programmed. So machine learning is a subset of artificial intelligence, okay? So they are all under the umbrella of AI. So that's why when you are building machine learning models and you become a machine learning engineer, you can say you are in the field of AI. So that's it, because machine learning is a subset of AI. And deep learning, which is outside the scope of this course, is a subset of machine learning. So when you finish this course and you want to grow beyond this level, you can explore the field of deep learning, where you'll be talking about neural networks and all of that, but that is solely far outside the scope of this class. Okay, so let's focus on machine learning. There are basically 3 types of machine learning. Okay, we have what we call the supervised, the unsupervised, and the reinforcement learning. All right, so this class will mainly focus on supervised. Yeah, in our other premium courses, we focus on both supervised and unsupervised. But for your class, we only focus on the supervised class. And what makes it supervised? What do we mean by supervised learning? Is actually, let's look at it from a concept of teacher and students. Okay, so the student, like for instance, for this class, I happen to be your teacher, so I can guide you. You will see that sometimes in the breakout section, okay, you have a guide. Maybe Dimeji is there or Shehu is under. So Dimeji could be your guide. He's the teacher there. So now he's the one guiding you as, okay, this is what is expected. This is the example of what your answer should be like. This is what we are expecting, things like that. So when you have a data and you have an example of the output that you are trying to predict, that example of that output that you are trying to predict is what we called, that is what we stand as the teacher or the guide that is going to guide the algorithm as to how to come up with its rules. So when you have that example of the output, it is called a supervised learning problem. Let me give you an instance. Let me give you an instance like this. So let's say in a particular data, so you have, let's say in your data, let's say you have like 2 variables, which are the goal is to predict the housing price. Okay, so that's the goal of this the model you want to predict. You want to predict the price of houses, maybe in Lagos, for instance. So you want to consider some variables like maybe the population of that area. Okay, so let's put that as pop. That's a variable that is part of the model that you want to build. You also want to consider maybe the number of bedrooms. So let's put that as BD. Okay, the number of bedrooms. Okay, and maybe we also want to look at the number of rooms entirely, because there could be rooms different from bedrooms. Okay, so let's put that as RM. And then we put an example of the output that you want to predict as price. Okay, so now so when I was talking of example of the output that you want the model to predict, remember the goal of the model is to be able to predict the price of houses. So we have values here, we have values, we have values, we have values, values for all of this. Now, because we are supplying, we also have values here, because we are supplying this column as price, which is an example of what we want the model to be able to predict. This price column is going to serve as the teacher or the guide to the model that we are trying to build. because this is an example of housing price, and we are building a model to predict housing price. So this will become our output or the target. Okay, that's become the target. So whenever your data has a target column, that is an example of the output that you are trying to predict, that problem is a supervised learning problem. In other words, that name comes from the data that you are given. If the data does not have this column, if it doesn't have anything to guide it, you only gave it features from year to year, then that becomes unsupervised. So what makes it supervised is because in the data, you have an example of the output that you want the model to predict. If that example of output is missing in your data, then that becomes unsupervised. Is it clear? Hello?
Yes, sir. It's clear.
All right. Okay, so apart from Dimeji, Dimeji, you already know this thing before. So is it clear to everyone else? Is it?
Yes, sir. Yes, sir.
All right. Okay, great. Okay, so that's that about supervised and unsupervised. So I put an example of like an application of these supervised and unsupervised. For instance, one example is one I use as example, like you want to predict the price of houses. That could be an example of a supervised learning problem. Or you want to identify fraud. Maybe you are building a model for a bank to identify a fraud, or an investment bank to identify credit card fraud or a fraudulent transaction. So you want to build a model to predict whether a fraud has occurred or not. Or you want to build a spam filters to filter an email as either spam or not spam. Those are supervised learning, because to build that in your data, you are going to have an example of the target that you are that you want the model to be able to predict. Sorry, if your mic is on, make sure you are muted to avoid okay. So, but unsupervised. So example of it is clustering, even though I won't go into the detail of that. Like you want to, for instance, what you see going on, if you have ever used, even YouTube does that if you observe that if you watch a particular video on YouTube, it begins to suggest similar videos for you. If you are observant, that's what we call machine learning going on there. It clusters. So what it does is that it doesn't have the example of the video you want to watch. It doesn't. But from the one you watch, what it does is that it's going to group all the videos that are available in its own search engine. There is an engine they are using. It's going to check for similar videos. It's going to group all their videos into different sections, and it's going to pick the one you watch and look at which section, which group is similar to the one you watch, and then it's going to suggest that to you. That's clustering. And they can use that in marketing, even in a supermarket. For instance, I can't remember any big supermarket in Nigeria for now. ShopRite, okay, yeah. ShopRite, for instance, if they have different sections of their goods, they can actually, you can build a model to cluster all the goods. I don't know if they do that, but I think if you watch, they have different sections for their goods. Maybe there is the electronics, there is this. How do they know which one should be closer to the entrance of the door, the entrance? Because it has to be goods that customers have been buying frequently so that they won't have to search too far, or something they feel is moving and is very attractive. So you can build a model to cluster those goods, and so that based on how frequent those goods are being bought, that's the one that we are going to determine, that one that is going to be frequently displayed, or the one that will be close to the entrance, things like that. So that's clustering. It has a lot of real-life applications. Industry use that. It's just that the most common one is the supervised learning, and that's because it has labels. Though there is another one coming up, which is the semi-supervised, but these ones are far beyond you, and that's when you have a data, some of the labels are present and some of the target are not present. So you are using the target present to predict the ones, the data that you are using that to predict the ones that are not present. But for now, just stick to supervised learning problem. Oh, sorry. So let's look at some machine learning terminologies that we're going to look at today. So you have a data. The goal is to build a model to predict whatever outcome that you want to do or you want to get. So you are not just going to throw the whole data to the algorithms and build a model. There should be a way for you to verify whether that model is actually good, whether it's performing very well. So that's why when you get the data, you are going to divide the data. People use two sets. They divide it into two particular parts. One part is used to build the model. The another part is used to check the performance of the model. But in the industry, you mainly use three sets. You will use one part to build the model, another part to adjust, to make the model get better, to adjust some of the parameters of the model. Maybe the model is not doing so well, you can adjust some settings there. So, and then the last part is now used to, when you are now done with all the settings, you are okay with the performance, you now use the third part to check the performance of the model before you put it into production. Now, the part that you use to build the model is called the training data. So that's the part you use to build the model. So the model will always do very well in it because that's the part that you use to build the model. The second part, which I said, is used to adjust the settings, to adjust the settings to improve the performance of the model. It's called the validation set or validation data. And when you are now okay with if the settings you've adjusted is now giving you a very good result and you are okay with that result, you finally use the third set, which is the test set, to finally check the performance of the model. Most times we don't want the model to see the test set until you are done using the validation data to adjust the settings. Okay? Anybody, why do you think we don't want the model to see the test set until you are done using the validation to adjust the setting? Why? What if the model sees this? Is there any implication? What do you think? Anybody?
It might the model will cheat.
What?
I said the model can cheat and it will not be actually accurate.
That's right. That's a very good one. So for instance, if you are in a class, suppose, I don't know if you are all still in school, but suppose that you are taking a course, and then you did a test, you did a test and then you didn't do very well. And then you are corrected, you are given the correction. And 2 days after, you are given the same test, the same question. Now, you are going to obviously do better than the previous one, the first one. That's the validation. You have adjusted you've looked at the mistakes. Okay, this is where I made some mistakes. This is where I made some errors. Okay, and then you've corrected it. And then you did again. You didn't get 100%, but your performance was better. And then you were corrected again that, okay, you should have done this, you should have done this. And maybe 3 or 4 days after, you're given the same question. You are obviously, in the long run, you are going to get better and you will do very well. But does it mean you've really understood the concept? What if you are now given a new question based on those same topic? you may do very well, you may not do very well. So that depends. So, but if the fact that you are seeing the correction of those, or if you do not give you a different question, the fact that you are seeing those questions and all of that, and you are being corrected, and over time you will do very well. And that's what we call cheating. Like you just know it over time. So that's the danger of exposing the testing set to the model. If you expose the test set to the model 1 time, 2 times, 3 times, after some time, it's going to understand the patterns in the testing data, and it's going to be giving you very good results. But that doesn't mean that if you give it a fresh data with the same variables as the training data, that is going to do very well. That doesn't mean no. That's what we call data leakage. So we don't want information to be leaked from the training data to the test data. Okay, so that's that. All right, so I think I've explained these 3. So in summary, so you have a data. If you want to build a model, you have a data. The minimum is that you split it into training or testing. But remember, in real application, and even in your projects, you should use 3 sets: training, testing, and validation. I will show you an example of how to split your data into 3 sets and also to 2 sets. But mostly we'll be using 2 sets, but I will show you on how to do it into 3 sets. Because your project, you are going to use 3 sets. So you split the data into training and testing. You use the training to build the model, and then you use the test set to validate the performance of the model. Okay? Any questions so far? Is it clear up to this point?
Yes, sir.
All right. So, so what happens when your model performs very well on your training, the data that is used to build the model, but it doesn't perform so well on the testing set or the validation set? What happens? What do we call that? What are you going to do? So when your model, because it's possible, the model will most times perform very well on the training because that's the data that is used to build it, okay? So when your model performs well on the training set, but it doesn't perform well on the testing, it is called overfitting. What happens underneath is that either the model is too complex for the data that you are giving it, okay? So it may be too complex. So if the model is too complex for the training data, maybe the data is not too big enough, or, so because overfitting means the model perform well on the training and not on the testing. But why will it perform well on the training and not well on the testing? That could be that the model is too complex for the training data, the data that was used to build it. So what now happens is that it memorizes all of the patterns on that training. But when you give it test data that it hasn't seen before, it actually did not understand it. This would have happened to you as a student in school. Like you are given notes, and this professor or this lecturer normally repeats questions from the notes. So you didn't really understand the concept, but you've memorized those notes very well. And you've memorized that if we ask you anything in the notes, you can explain, you can say everything because you've memorized, but you didn't really understand it very well. So if instead of bringing questions from the notes, the lecturer now give you questions from the same topic, but not from the notes. I know many of you would have experienced this. And there is high tendency that you will not do very well if we give you questions from a different, not from the note, but from the same topic. There is high tendency that you will not do well. Has anybody experienced that? People don't want to. Okay, so I have experienced that in the past. So that is it. So that's what we call overfitting. You've memorized, the model has memorized all of the patterns in the training because it was too complex than the training data. But when you supply it a fresh data, it may not be able to understand the patterns in it. Now, underfitting is just that the model is too weak. The model is too weak compared to the data. So it's too weak to capture the patterns in the training data. So that means the performance on the training is poor and the performance on the testing is also poor. But generalization is what you want. That's when your model performs very well on the training set and it's also performed very well on the test set. The test set is what it hasn't seen before. That's the model you want. And that is the one at the middle. That's the one we call the good compromise. If you look at the overfitting one, see what I was saying, that the model was trying to capture everything. The model was actually trying to capture all the red points. You can see how it's trying to make sure that it clearly separates all the circles from the plus, meaning it wants to be perfect. So it memorizes all the patterns. But in the way of memorizing all the patterns, it also memorizes noise, some things that are not useful. That's because the model is too complex for that model. But underfitting is, the model couldn't, because the goal is to separate the circle from the plus, and that's why it's making sure in the overfitting to clearly separate it. If you look at underfitting at the far left, the model couldn't clearly separate them at all. So it's too weak for the data. But the good compromise is what you want. It can make some mistakes, but not very well. So, but this good compromise, the model generalizes well. So when you hear that the model generalizes well to the training data, it means that the model performs very well on the training data and also on the test data. And that is what you want. Any question? Any question?
No, sir.
All right. So the question is, when there is overfitting, how do you think we can solve it? Let's talk. If you truly understood what we've just explained, how do we solve it? Remember overfitting? Okay, go ahead.
You can change the model. Since overfitting is
change the model. What do you mean by change the model?
Okay, you explained that overfitting is when the machine learning just memorizes the previous the testing model. So, and it never understood it. So I think how to deal with overfitting is to maybe change the model and then or create a validation data where you test the model before you now try to the real test data. I don't know if that is the case.
So, for instance, now, let's say the goal is to build a model that can classify an image as either cat or dog. And the name of the model is called logistic regression. Now, there are different models that can also do that classification, maybe random forest, support vector machine, or even neural network. So are you saying that if I've used logistic regression and it's overfitting, we should change it to, let's say, a model like other model like random forest, support vector machine? Is that what you're saying?
Yes, maybe it should, maybe.
Okay. All right, any other person? Thank you, Sammy. Yes, any other person? Awele, what do you think? Awele, are you there?
Yes, I'm here.
So what do you think?
I said, since the problem with overfitting is that your model might be too complex.
Mm-hmm.
So maybe you would have to kind of simplify it. So
that's a good point. That's a good point. Yeah, we're going to talk about how to do that. So that what our LA is trying to say is that since we said overfitting is also when the model is too complex for the data, can we reduce the complexity? Yes. And that's a concept called regularization. We'll talk about it later. So that's one, which there are other ways. Yes, who else want to try? Joseph, do you want to say something? Ayomide, Rafiu, or Fumbi? Any one of you? Yes.
Can we try training more data?
more data assets.
That's a very good point too. So in fact, if you are talking to someone who does statistics, the first thing they will think of is, can we get more data? That's it, because we said overfitting is actually caused by either the model is too complex for the data. By too complex, we mean maybe the data is too small compared to the model. So there is always that conflict going on in building machine learning model. You know, the question some people will ask, how do we know when the data is big enough to build the model? Over time, you will just have an idea. But the point is, if it is possible, get more data. The bigger your data, the more your model will perform well. So that's a very good one. So basically, there are two major ways. Get more data if it's possible. Though getting data in the real world can be very expensive. But if it is possible, get more data. And two, can we reduce the complexity of the model? Can we simplify it or regularize? By regularization, I will explain it later, is actually to adjust the parameters of that model, the hyperparameters. Okay, so those are the basic, those are the main two ways. Get more data if possible. You can see regularize the model, which is simplifying a model that is very complex. So what of underfitting? Yes. How do we resolve the problem of underfitting? Anybody?
Well, since overfitting was adding more data, I was thinking maybe you remove some redundant data in it.
Adding, so you are saying, what do you mean by redundant data?
Some unnecessary.
Maybe like data cleaning.
Can you explain what is it?
Okay, so okay, what I meant was that, like, since overfitting was if we didn't have enough data to like simplify it, like, enough data to differentiate. I'm thinking underfitting is maybe there's too many clusters of. I'm just using logic here. Like, there's too many. There's too many clusters, and then we see similar data sets that we can actually remove as they might not be useful in the whole thing.
Oh, okay. Yeah,
Let me pick it from. I want to pick it from where it stopped.
Okay.
Something similar to what he said.
Right.
Something like doing a data cleaning.
Okay.
Something like taking away the outliers. If there are too many outliers, or something like that.
Okay.
More or less like work on the data to get rid of those outliers so that we can then have a clean data to work with.
Okay. Yeah, thank you, Joseph. Yes, who else? Who wants to try?
The underfitting said maybe the model is too weak to capture the pattern. So possibly
Say that again.
Then underfitting is when the model is too weak to capture the pattern.
Yes, too weak to capture the pattern in the data.
Another model.
What?
I said you can try other models for the data.
Oh, okay, that maybe that particular model that we're using is too weak to capture, so we should try another model. Is that what you're saying?
Yes, sir.
Oh, okay. Thank you. Yes, one last person.
In underfitting, I feel that you still need more to get more data, because the more data you have, the more testing, the more you can run it.
Okay, thank you, Fumbi. All right, so you've all spoken well, but now let's look at it very well. Underfitting, we said, is when the model is too weak to capture the patterns in the training data. So it's not a question that you don't have enough data, but the model is weak. It's weak to capture the training data. Okay, look at it, for instance. You did a course. You don't even understand the notes. You don't understand what the man is saying. So you don't even, and you can't memorize it because it's full of a lot of provings that you can't memorize. And so you don't understand the one in the notes. So even if he gives you the one from the notes, you won't get it well, let alone of giving you the one not from the notes. What are you supposed to do? Is to find a way to understand the concept in the notes, right? So it's not to change the notes or if you change the notes and get someone else's, so maybe it's your own notes, you will still have the same problem because the same concept is there. So it's not a point of changing models actually or getting more data. Even if you change models, the problem is that the model is not, there's no one model that is complex than the other. No. What makes them complex is the parameters in the model that you can adjust. So the point is, you just need to increase the complexity. It's just the opposite of what Awele said there. In overfitting, we can simplify the model. In underfitting, increase the complexity. How do you increase the complexity? You can adjust the parameters. Maybe you reduce that regularization. You can adjust the parameters, so that the model becomes more complex instead of too simple to capture the patterns. So, if I want to borrow the idea of Fumbi that get more data, it will not be get more data of the same features. No, it will be adding more features to the data, more variables, not like more rows. It's like adding other variables. So that way, the model will become complex and the data will also become complex at the same rate. So it's either that's why I say increase the model complexity. How? By adjusting the parameters of the model. Okay? All right, so this is the part we're going to focus on today, which is on linear regression or linear or multiple regression. So regression is one type of supervised learning. If you remember the chart I showed that supervised can be divided into two. We have the regression, we have the classification, and I gave the two examples. The regression is the one, it follows the example I gave for predicting housing price, while the classification follows the example I gave for a model to be able to classify an image as either cat or dog. Okay, so but for today, we're going to focus on regression. So if your goal of building the model is to predict a numeric values, then it is a regression problem. Okay, so like predicting the price of houses, predicting weather data, or like the weather for tomorrow or the stock market price, that's a regression problem because your goal is to predict a numeric variables. Like you want to predict the views, how many views, or you want to predict the sales of a particular YouTube video, but you are using the views as a variable. So this one is just a linear regression. Why is it linear regression? It only have one single variable, and you are predicting using that one variable to predict the output sales. The variable here are the YouTube views. The output is the sales. So if your model has a single variable, that's linear regression. In the real world, linear regression rarely exists because most times you are going to have many variables. So when you have many variables, it's called multiple linear regression. Okay, so it's called multiple regression or things like that. You get? So linear regression is just a single linear regression that you just have a single variable. Okay, but when you have multiple, regression, then you have many variables. Okay, so but the goal is you are predicting a numeric outcome. But if your goal is to predict categories, cat or dog, fraud has occurred or fraud hasn't occurred, spam or not spam, those are classification problems, and we'll look at that maybe upper week like that. So but today we'll focus on just linear regression. I won't talk about, this is where I will stop. When you are talking of, when you build a model, so all the points, all the black points you are seeing, those are the original target, maybe the housing prices, the example of the output. The blue line you are seeing is that's what the model is predicting. The model is predicting the values that we use, that we draw a straight line through, but all those black lines, they are the original output in your data. So if you want to measure how your model is performing, it's just to measure the distance between your original output, those are the original housing price in your data, with what your model is predicting on this blue line. So that's why you see we draw a line from the dot to the line. So that difference is what we call the error. Okay, is what we call the error. That's the mistake your model is making. Okay, so if that, most times the goal of building the model is to reduce the error. For those that did statistics, that's what they are teaching you when they did least square. But is something that they don't really explain to you. But that's what all least square is about. But that's not the goal of this class, to teach the mathematics. Okay, so but the difference between what your model is predicting, that's this blue line, and what you have in the data, the original output, is what we call the error. Okay, and that's why we put that as it. So the goal is to reduce this error to the barest minimum. The smaller the error, the better the performance of the model. The larger the error, the weaker or the smaller or the weaker the performance of the model. So you want the error to be very small. Okay, so let's look at how to do all of these in Python. Let's look at how to use Python to take our data from whatever it is and then build a simple regression model. Before I do that, do you have any question on this? Is this one clear?
Yes, sir.
Okay, so let's see. Let's use, okay, so all those concepts, they're also in the notebook that you have, so I won't go over them. So this is the regression model I was talking of. This is the Y output, the Y, that's what you are trying to predict. That's, in this case, that's the red line. That's this Y hat here. All the X that you are seeing, X of 0, X of 1, X up to X of P, those are the variables in the data. So for instance, if you want to predict house, X of 0 can be the population in that area. X of 1 can be the number of bedrooms. X of 2 can be the number of rooms, things like that. Why? What the model is actually trying to learn or come up with are these weights, these W's you are seeing. Those are the coefficients. I know for those of you that have taken any statistics course, you must have seen this equation, but they don't explain. You are more or less like memorizing what those W's are. What this equation means. You see, this linear regression is a machine learning model. So the model, when you say machine learning in terms of regression, the model is trying to learn the appropriate values for these W's that it will use to predict this Y. So it is this W that the model is coming up with. Remember, if you have a data, you don't have W's there. X, those are the variables, and that's the only thing you have, and that's the only thing you are giving to the model. So when you run a linear regression model, the model is trying to come up with the values for these W's and this B, which you call the bias term, or some of you who have done they call it intercept. The model is trying to come up with those values of B and W's that will help predict the accurate value of Y hat. So that's what the learning is for the model. So if the model come up with wrong values, then it will make more errors. But the machine learning model must try to come up with very appropriate values of W to reduce the error it's making. So these W's are what they call weights or coefficients. For deep learning neural networks, if you decide to go higher, they call those W's, they call it weights. So you can call it weight and you can call it coefficient. All right? So I can show you from here. Now the data I'm going to use, you have it also in your Canvas dashboard. I'm going to use the housing data. All right? So the package, the library that you are going to be using for building your machine learning model is called the scikit-learn. Scikit-learn, scikit-learn, L-E-A-R-N. You can type that in Google. So that is the package. If you, there's no way you will talk about that. You build machine learning model with Python and you will not know about that package called scikit-learn. If that's the first question anybody will ask you, if you say you build machine learning model using Python, do you know scikit-learn? And that's what I put here. So it comes pre-installed with your Anaconda. But if you are using other IDE, like we're going to start from next week, you might have to manually install this scikit-learn by using pip install scikit-learn. Okay, so that's the package that you use for building your machine learning model. It has all of the different models there, and I will show you how to do that. So, like I said, the way I want to teach this machine learning session is I want to use function. I'll be using function a lot so that if you need to go and brush up your use of function, then you need to do that. Okay, so but this should be clear. I mean, all the steps will be clear. It's just that I want to use function because if you are in an industry, you want to build a model, or you are writing programs that they are going to push into production, your code will more or less be in functions. Otherwise, it will break it will break production, and that will show that you are not competent. So I'm going to teach you using function. So we're going to define different functions. So the goal, remember, the goal is to get the data. I'm going to assume that the data is clean. But if it's dirty, it's the same thing. You can write a function to clean the data. We'll show you all of this. But this particular data I want to use, we'll check it. I'm not sure. I think it's clean. So we're going to write a function, different functions. So maybe the first thing, I mean, let's load the data so that you can see. This data is called housing. So we have import pandas as PD. Remember, to work with data, you import pandas as PD. This is the URL where I have the data. Okay, so let me call the variable housing to own the data. So you do PD dot read underscore what? Yes?
Read underscore CSV.
CSV, and then you pass in the URL. So let's see the first 5 of this data. So you can see the data. So these are acronyms for variables in the data. Okay, so RM stands for like the average number of rooms. This is the average age of the house. Okay, I'm not sure if I know the full meaning of everything. Okay, but normally there should be a metadata that explains all the variables. But I know this is the average number of rooms, this is the average house of the house, and the average age of the house. Okay, but this is what we are trying to predict. This the median price. So that's the example of the target. So that's what makes it a supervised learning, the median price of the house. And that's what we are trying to predict. And since we have it in the data, then that means it's a supervised learning. So let's check if it has any missing values. If it doesn't have, then we don't need any data cleaning for now. But in your data, trust me, in your project, you are going to clean the data. Okay, so there's no missing values. Okay, so what I want to do is I'm going to write a function. So the first thing we're going to do is write a function that accepts the URL, the data URL, and so that's the input. So the function will accept the URL, and then it will load the data. And then, because remember the goal, when you get the data, we also want to split the data. Remember this PowerPoint I showed you in your, to build a machine learning. So our function is going to get the URL for the data, is going to split the data into training and testing, and is going to scale the data, because before you build a model, is always a good practice to normalize your data. This is because by normalization, we mean we want to bring all the variables in the data to the same scale so that no variable in the data will be dominant. For instance, let me show you an example here. Let's use describe to check the range of the data. Okay, let's use describe. Now watch. See the CRM is from, the minimum is 0.006 and the maximum is 88.9. Now let's check other variables. So there's another variable called tax that the minimum is 187 and the maximum is 711. So that variable alone can dominate the model. This one is even fairly simple. You will have some data that maybe one will be from 0 to 1, another one will be from 10,000 to 1 million. So the one that has higher ranges will dominate your model. So that's why we normally normalize the data before you build the model. So we write a function that accepts the URL, and then and load the data. So what other things is going to do is going to split the data into training and testing, and then it will normalize the data. So that's what the function will do. Is this task clear, what we want the function to do? Is it clear to everybody?
Yes, sir.
Yeah, instead of doing it one by one, you can actually do it one by one, but I want you to develop an habit of writing functions for your data. I mean, you can start out by doing it one by one, but when you want to put your project together before you submit it to the management, if you are working on industry, you need to put them inside the function. That will even tidy it. Okay, and that's what we're going to be doing in the other ID like Visual Studio Code, because you are going to install Visual Studio Code before next slide. So that's the thing we want to do. So first, we define a function. Let's call it processing or data processing. Let's just call it that. So remember how to define a function. So this function is taking in a URL, okay? So the first thing we said, load the data. Okay, so load the data. So, and that's basically what we've done here. Okay, so we can copy this and put it there. So then we've actually loaded the data. So it's the same thing. Remember, function is the same thing as writing one by one, but you are wrapping it inside a name. So here we've loaded the data. The next thing, we're assuming this data is clean, okay? So we want to split the data. Now to split the data, then we have to start using our scikit-learn, all right? So the same thing, to do that here, we have to import the function from scikit-learn that will help us split the data. So we'll do from scikit-learn model selection, from scikit-learn model selection, import, there is a function called the train test split. So it's going to split the data. So this is a function located in the model selection module in scikit-learn package. So this is a function. The model selection is a module in scikit-learn, but this model selection has a function called train test split. All right. So this function train test split is what will help us to split the data into the training and into the testing sets. Is it clear?
Yes, sir.
All right. So the first thing we'll do, so we want to split the data even before that, let's get, because this data has the targets there, we need to find a way to remove the target from it, like separate it so that we have features, that variables, and we have the targets separately. So we need to remove this target column, this MEDV, from the entire data, okay? So select the features and the targets from the data. Okay, so let's have the features. So the features will be in our housing. In our housing, we have, so let's just drop, let's drop the target, MEDV. Since it's the only one we want to remove, let's just drop it instead of manually selecting all the variables. But you have to specify that your axis is 1. Who can remind me why you specify axis to be 1? We did this on that data. What?
So that I won't drop the rows there.
That's right. So that it will not drop the rows. It's going to give us error because it can't find MEDV in the rows. So you have to let it know that we are talking about a column. That's good. So we can do that. And if I want to convert this to a NumPy array, I just need to do dot values. Okay, but this is not compulsory. For large amount of data, it's a good idea to convert it to NumPy arrays. Who can tell me, who can remind me why we said one advantage of NumPy array? Why it's fast? That's right. So you guys are good. It's fast. So it may not really show for this small data because this data is small. But for the data you're going to use for a project, it's going to be very large. You may try to convert it to, you may develop an habit of turning the features to a NumPy array by doing dot values at the end. But even if you don't put it, it's still going to work. It doesn't mean that you must do that. Okay. Then we can also select the targets too. So we have the housing, and then we just select the MEDV. Okay. Then we can also do dot values too. Okay, to convert it to a NumPy array. So we've gotten the features and the targets. So we need to split the data now. So split the data into training and test sets. So what we'll do is, let's call the training, let's use the X for the features. Okay, so this will be X train for features, and this will be X test for the features for the test set, and Y for the targets, Y train, and then Y test. So we'll call the function that we imported now, this train test split. Remember, we imported it from scikit-learn model selection. And then we'll pass in the data we want to split. We want to split the features into X train and X test. And we want to split the targets into Y train and Y test. Now, by default, this train test split, we use 75%. It will divide 75% and use 75% for training and 25% for test set. The same thing for the target. By default, it's going to do 75% and 25%, but we can change it. If you want, you just specify the test size to be whatever percent. Maybe if I put 0.3, so it's going to pick 70% for training and use the remaining 30% for testing. But if I don't specify it, we use the default value. Is it clear?
Yes, sir.
Okay, then finally you specify what we call the random states. So I'm going to use a value of 0, but it doesn't mean you can use any number. So random state is just like a seed. What do I mean by a seed? Like, I want for reproducibility. If I don't set this random state, this train test split is a random function. So every time I run it, it selects different number of rows for the training and test different times. So if you don't set it, your model, every time you run this, is going to select different number of rows for the training and test set. And that means the model, the performance you got before, if you want to show me tomorrow, let's say you have a class tomorrow, it may not be the same. So it's best to set the random state to a particular number. It doesn't have to be 0. I just like using 0. So that way, even if you run the model, this function different times, it's going to be selecting exact number of the same rows it selected before. It's just like a seed that you are setting for reproducibility, just to make sure that you are selecting the same data every time. Okay, so that's what the random state is. If you don't put it, it's not going to get the error, but you are going to be it's selecting different data at different times. So we've done this we've split the data. Now we want to normalize the data. So meaning we want to normalize. So to normalize it, I've explained what normalization means. I said it means bringing all the different variables in your data to the same range. Because if you don't do that, variables with higher range will dominate your model. Okay, so to do that, there's also a module in scikit-learn that we can use. So from scikit-learn pre-processing, there are two major ones. There are many, but there are two popular ones. One is called the mean mass scalar, and one is called the standard scalar. So you can use any one of the two. You don't have to import the two. I only want to explain the two. That's why I imported the two. You only need one of them. Now, what mean mass scalar will do is this. Let me write on the screen to see that, to show you. So suppose you have a data this way, okay? Sorry. Okay, so suppose you have a data this way. Let's say this is the first variable, okay, x1, and this is the second variable, x2. So suppose you have, this one is 20, this one is 59, and this is 5. And then this one is just 0.2, 0.5, and this is 1. So if you want to use mean mass scalar, from what it does is that it's going to work on each variable separately. When it's working on the first variable x1, so what it's going to do is that from each value in this x1, it's going to subtract the minimum value, which is 5 from here. Okay, it's going to subtract the minimum value and divide it by that's each row minus the maximum value. So this, what I'm saying is, it's going to pick 20, like divide it, 20 minus 5, 59 minus 5, 5 minus 5. That would be and then it will add them together and then divide it by, the maximum is 59, 20 minus 59, 59 minus 59, 5 minus 59, and sum them and divide it. So it's using the mean mass scalar. So it's subtracting the minimum from each variable and dividing it by the maximum, the maximum that is subtracted from it. So that's what it's going to do also for the second column and all of that. But the second column will be based on the column. So that way, all the values is going to be, by the time you apply, all the values will be in a range of 0 and 1 by the time you finish it. But for the standard scalar, it's going to use the concept of statistics. What it's going to do is that it's going to subtract a mean of 0 from each variable and divide it by the standard deviation of 1. It's going to do that for each of the variables. So that way, all the variables, we have a mean of 0 and a standard deviation of 1. So that's the idea of normalization, but you can use any of the two. None is better than the other. So I will use the mean mass scalar. So I will define I will save a variable called scalar and have mean mass scalar. So this is creating an instance of it. I'm only instantiating it. So let me just do instantiate the scalar. You can see how I'm commenting. That's how you should be writing. So instantiate it and then normalize the data. So to normalize the data, we're going to normalize the training and the test set. So let's call it xtrain std so that we can still have access to the xtrain. So this will be the scalar that we've just created, the fit transform, and we'll pass in the xtrain that we have. So let me explain what is going on. So this xtrain is this that we want to normalize. What is fit transform doing? You see that calculation I showed you. If I've only called fit on it, that's the only thing it's going to do. It's only going to calculate the minimum and the maximum of each of the variables in the data. But nothing will happen. It's not going to transform the data, but to change it, to use the minimum and the maximum that it calculates to adjust the variables in the data, that is what the transform is doing. Is it clear? Hello?
Yes, sir.
All right. So I know this is a lot of information, but you will get it as we move on because we're going to be doing this almost every time. Okay, so then finally, we're also going to do that for the S test, but for the S test, I don't need to find the minimum and maximum again. I only need to use the minimum and maximum that we calculated from here, from the fit, to transform the S test. So I will just do scalar dot transform. So for the test set, you don't do fit transform, you only call transform. Okay, because if you call fit transform again, that means you are going to find another separate mean. And that way the two data will not be similar. So the model will not perform very well. That's all. So once we are done, we only need to return. We just return the two things. What are the two things? The xtrain, std. We also want to return the s-test, std. We also want to return the y-train and the y-test. That's all. That is all. So when we call this function in a separate cell, this function will return these four things for us. So, and this is what we use to build the model. That's all. Any question here before I move on? Is this function clear to everybody?
Answer the question.
Yeah, but there is a lot of noise from your hand. So, okay.
Can you hear me also?
Go ahead.
The question is why are we not transforming the white train and white text also?
Okay, so yeah, I'll answer it, but please mute because there is noise from your background. Okay, so we don't need to transform the output. The output is what you are trying to predict. Okay, this is an example of what you are trying to predict. So it's not really necessary to transform the output. Okay, because that's what you are trying to predict. Okay. Any other question? Okay, so that's all. Let's run this and let's see if our function is working. So we have the xtrain. So let's call it, if you like, you can call it the same name, doesn't matter. So, or if you, XTR, that depends on you. Let's call the test set STX and the Y-train, YTR, and this YTX. It doesn't have to be the same name. So I will just call the function the data processing, and then I'll pass in this URL that we've defined here. That's all. So I'll pass in the URL. So let's see if there's any error. No error. So let's check what is in XTR. So let's check the shape. You can see. So this is, you can see that there's something there. So it's saying there are 13 variables, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then 13. That is it. So you can also check the shape of the S-tests. You can see. So the data is actually very small, and that's because we have split it. So one is carrying 379, one is 127. And if you want to check what you have there, so maybe you want to check the first three. See, that's the data. So you can see that the function is working. So that way, that saves all of that, makes your code easier to manage. And I don't need, so I can use this function different times. The only thing is that I can actually, except I code this, that I can code the data. If there is a generic name called target, I can, doing that. I can actually specify that this should be a target. Like for instance, I can do, maybe I say this is target. So if I now want to do this, I will have to specify the target. So in this way, I would have said, I'll just remove the whatever the target. So I can use this function for another data, for another model. I can actually do that and just that, okay, whatever the target is, so that you don't hard code it, whatever. So I will have to specify the target here. So the target will just be a name that I'm putting there, maybe like MEDV. Let's see if it will work. So it's not working because it said, okay, I didn't run the model, I didn't run this function again. So let's see. See, it's still going to work. You see? You see that? So that's it. So we can just give that, okay, it takes a URL so that we can reuse this function, because this function, if I want to do build another model, that I can use this function. I only need to import the function that I've defined. I can use it in many different scripts. And that's why we will use other IDs so that you can begin to see this. So this way, it's going to take the URL and whatever target I drop, it's going to use. So the target is this particular value is what we put here, because I know the data in the data, MEDV is my target. That's what I drop here. Hello, can you be muted? I don't, there is, okay. So that's what we drop. I can give it another name if you want, if this particular one will be confusing to you. I can call it label. Okay, so can call it label. So that means we change it label here. So whichever one that you call it, just keep track of what you are doing. So that's just it. So so the label, that's what you are trying to predict, and that's, so here we drop it, is the same thing. You drop it from the data, and then we load it to get the target and all of this. So if I do this, it's going to give me the same thing. You can see no error like that. So this is it. You see? So is the function clear to everybody? Is it? Or is it confusing?
Yeah, very well clear.
All right, so that's the approach we're going to be following. So now to build the model, we can even define the model into another function, and we'll call this previous function. We will not need to call the function here. We can define another function to build the model, and we will call this function inside the function to build the model. We can do that. So we can define a function called module. So that's our module. So let me use capital letter. So that's a module. The function should take in, maybe it's taking nothing. Over time, if you learn more models, you can even run, you can use different models. So that means we're going to give it a name, like maybe model name or things like that. But for this time, let's just use, suppose that we're only going to run a single model. Okay, as we go on, we will develop this concept. So it's not taking any parameter. So the first thing is we want to get the normalized data, okay? This one, people are quiet. I hope we are not, I'm not, okay. So get the normalized data. So the data is this. So let's just copy all of these. Let's copy it and put it here. Okay, so we have, so this way we've passing, you can say I've called this function that we define up to help us get the data and process it. I've called it here. So when I call it here, it's going to return the process data. So this process data is what we want to pass to the model, but we need to import the model. So since we are using linear regression, we can get that from scikit-learn also, from scikit-learn linear model. So we import the linear regression. Okay, so after getting in the data, let's instantiate the model. Instantiate the model. So we have the linear model, which is, let's call that LR or LM, whichever one. So I will instantiate my linear regression model. That's all. Then the only thing I need to is to train the model. Remember, we train it on the test set and validate it on the, we train it on the training set and validate it on the test set. So train the model. So to train the model, I will just call the lm.fit, and I'll pass in the training data, which is str that we got here. If I'm too fast, please let me know. I will pass in the target YTR. Someone is trying to write on my screen. Fumbi, please.
Sorry, sir, is a mistake.
Yeah. So this we train the model. That's all. So to validate, to check the performance of the model, we can actually do that. We can check the performance on the training set and on the test set. We can do that. So if we want to check the performance on the training set, so there are two ways. I can decide to put it in a variable and then return it. Or I can decide to just print it out to the screen so that I don't need to return it. So I can do like print. So let's make it beautiful. Let's call it training. So we're going to use the accuracy, training accuracy. So I'll just use a placeholder where I'm going to put the value there. Let me make it 4 decimal place. So I'll do dot format. So format my result. So to get the accuracy is just, you call the model that you have built, call LM, and you call the score method, dot score. So that score is what will give you the accuracy of the model. So you want to dot score, and then you pass in the training data, which is str and the training target. We'll do the same thing for the testing so as to see the performance on the test set. But remember, in real life, this second one is supposed to be validation, not the testing. Okay? So I will just change this to be X test and this to be Y test. That's all. So that's all. So I just need to, so let's run this. I just need to call the function, which is the model. So in that case, we will not need this one again. I only showed you before just to see it, and we will not need this one again. So let's just call the model. Once I call the model, this one we call the previous function. That is it. So okay, so I'll call this model. So this model, so once we call the model, that's all. Well, I mean, we could have even called it linear regression model. We could have called it just to be specific. And then here we just call reg model. Let's see. So he said it's not defined. Oh, there is a mistake in the spelling. So you can see the training accuracy is 776 and the test accuracy is 63. So So that's just it, you know. You see that? So is it clear? Let me ask questions so that I can explain. I can explain whatever is not clear. Any question? Is it clear? Okay.
Can you explain why the training accuracy is? Like, can you explain those value differences? Why are they different? Or like, what do they mean exactly? Those values?
I can hardly hear what you are saying. There is noise in your background.
Sir, can you hear me now?
Yes.
I said, can you explain those values, though? Those accuracy? Are they telling us that, like, that this training, this model was able to, like, I don't understand those values? How would
That's a question I want to push to you guys. What do you think this, from what I've explained, what is this value? What does it mean to you guys?
Okay, let me try to answer that.
Okay.
So from the training accuracy, since we had the MEDV column, we had the values already. So we are training the model to try to predict the values, having those columns, having all those data. So I think the training accuracy is more like the model was able to predict 0.76 predictions out of 1. Like it was able to get so close to the values you have in that MEDV column. While the testing accuracy is now like, since it has tried to predict that one, yeah, since it has learned with that one, so how well can it now try again with the testing accuracy? So the testing accuracy was now less than the training accuracy.
Okay. Okay. Who else want to try? Who else want to try? Nobody. So what this is saying, just like you explained, but what this is saying is about 76% of the time, this model, I mean, we're mainly focused on the testing, okay? This is about 63% of the time, the model will correctly predict that housing price. So the model is performing, like the performance of the model is about 63%, meaning in about 63% of the time, this model will correctly predict the price of a particular house. Okay, so that means this model, you know, so can we conclude? Can we say this model is not doing well? If it's not doing well, is it overfitting, is it underfitting, or is it generalizing well? Anybody?
Sir.
Yes.
I would say from my own side, I would say the model more like generalized fine or something. I'm not sure.
Is that generalized well?
Yeah, I'm not sure.
Okay.
Or let's say on that, since the testing accuracy is below the training accuracy. So can we say that as underfitting, more like the model is weak to predict better or something?
Okay, who else?
Okay, so I think is overfitting because the training data is doing a lot better than the testing. The training accuracy is a lot better than testing accuracy.
Okay, so logically speaking, we can say this model overfit because the training is higher than the testing. The training is about 76%, the testing is about 63%. So since the training is doing better than the testing very well, we can say that this model overfits. However, given the size of the data, we should expect this to have happened, okay? Right? Because the data is very small. Look at the data we're using. The data, I mean, when we check the data, it was about, the training was about 300 and the testing was about 120 something. So the data is small, so we should expect that the model will overfit. If you remember, we said that when the model is too complex compared to the data, then that model is likely to overfit. So that means the model is complex than data. And I remember you said, I will suggested that, okay, it was Fumbi that we should increase the data or regularize the model. So since we cannot adjust we cannot get more data, what we'll look at next week is how to better option to regularize this model. So we can say this model overfits. Okay, does it make sense? Yes, so, but if you look at, at the two functions that you define, one function to process the data, the other to build the model, is it clear to everybody?
Yes, sir.
All right, so we might not be able, I mean, next week we'll go far and then we'll be able to do all of these exercise. So I've explained some concepts, I will still re-explain and all of these ones. So by next week, by God's grace, we'll be able to see how we can resolve this issue if it is possible. We'll explore the two other models that can help us do the regularization, which is the lasso regression and the ridge regression. And that will be all for regression. But we're still going to stick to the idea of using functions. However, during the week, I'm going to send you a link, or you can just directly install Visual Studio Code, but I will send you a link to download and install it so that you can be used to other IDs, so that we can be able to call different functions from different scripts in our code. Any question before we go? Any question before we go? If there is no question, well, this is where we're going to stop. All right.